Okay, so hopefully you're all ready for some nice small mathematics and data assimilation just before lunch. In fact, some of what was said in Julia's lecture will provide useful background to some of the things that I'm going to talk about today. But I want to start by just summarizing where we got to yesterday and trying to say, okay, if you didn't follow all the details yesterday, what is the core of what we're trying to do? And we're trying to say we've got some model state X, which could be our fluxes, it could be a weather model with all the grid points of pressure and temperature, it could be an ocean model with all our values of the temperature and salinity of the ocean. We have some state X. And we still have some prior estimate of the state X, which we call XB, which we assume to have a covariance matrix P. And we have some observations of the state Y, which we assume to have a covariance R. And then what we've shown is that our best estimate of the state, we said, could be found by minimizing this cost function. Now, we used some Bayesian arguments to get to this. I'll show in a moment a different way, a more thinking of the dynamical systems way to get to the same idea. But essentially we have a least squares problem where we're trying to find the state X, which is close to our background, weighted by the inverse of its errors, and is close to the observations Y, weighted by the inverse of its errors, where this H maps our state to our observations, so converts our model state into the equivalent of what we're seeing in the observations. One thing I mentioned yesterday, but I understood talking to someone last night was maybe not clear. If this H is linear, then we can write down an exact solution of this. Where does this come from? Well, if H is linear, we can easily form dj by dx, just write down the gradient of j. And if we write down the gradient of j, the gradient of this function here, and set it equal to 0, because at the minimum the gradient must be 0, then by just some rearranging, we can end up with this equation here. So the exact solution when we have a linear case. And so what we're going to look at is ways of solving the variational methods, which Julia spoke about, which use this first formulation, and also some of the Ensemble Kalman filter methods, which use this second way of solving the problem. And then the practicals that you're going to do today and tomorrow will be using these kind of methods. So in variational data assimilation, we said yesterday, we're trying to find the solution that maximizes the a posterior probability, P of x given y, which we showed was proportional to this, or is equivalent. This, since we have the exponential of something negative, it's equivalent. Finding the maximum probability is equivalent to finding the x, which minimizes this cost function. A couple of inconsistencies I've noticed slightly. Sometimes we put the half in front of this cost function, and sometimes we don't. In a sense, it still has the same minimum whether the half is there or not. Just putting the half makes things easier a little bit when we write the gradient down. And I've noticed sometimes I put y minus hx, and sometimes hx minus y, but since we're essentially squaring it, once we square it, the order doesn't make any difference. So if you notice some inconsistencies with the way I've written it, this is why. It should be the same. So the variational data assimilation, we say, okay, what we want to do is find the x, which minimizes this cost function. Let's just use some numerical optimization to find that. And we consider two main algorithms, three-dimensional variational assimilation, or 3D VAR, where we consider 3 dimensions, the 3 space dimensions. So we're considering doing this problem where we've got a model in 3 spatial dimensions. So say like a weather forecasting or an ocean forecasting model. And then there's also 4-dimensional variational assimilation, or 4D VAR, where we consider not only the 3 spatial dimensions, but we're also considering time as a 4th dimension. So we're considering observations distributed in time, whereas 3D VAR considers observations just at one time. And in that case, we consider the observation operator as including also our dynamical model. But hopefully this will become clearer in a moment. So I'm going to present first 4D VAR, and then 3D just as a simplified case of this. So the aim of 4D four-dimensional assimilation, is to find the best estimate of the true state of the system, the analysis, or this maximum probability state, which is consistent with both the observations distributed in time and the system dynamics. So if we consider over some time window, T0 to Tn, we have observations yi of our state x. And this, say, in weather forecasting, will be a 6-hour or a 12-hour window, for example. And we consider that at the initial time, we've got our background or our prior estimate of the state. And if we run the model from that state, we don't fit very well what happened in reality. So what we want to do is to find another state close to our background, our prior, because we know our prior is reasonably good, but such that when we run the model, we get a better fit through the observations. And if we do that, then we can say that from here, we would expect our forecast to be better, because over that time window, we've actually matched what happened in reality. So how we're going to do this, I'm going to consider this from a dynamical systems point of view now, or least squares, but we'll see it gives us the same as the Bayesian solution. We're going to set up a function which measures the distance to the background, or prior, weighted by its errors, and measures the distance of this trajectory to each of these observations, summed over all the observations, weighted by the observation errors. And so that gives us a similar thing to the cost function we had before, where we have a term measuring the distance of our initial state x0 to the background, weighted by the inverse of its errors. And here I've replaced the P by a B matrix, because in the variational, we assume, I mentioned yesterday, we assume that this prior covariance matrix doesn't change with time, and so we just use the constant B rather than P we'll see later in the Kalman filter for one that's changing in time. But this is essentially what I had before. And then we've got the sum over all the observation times, where for each observation time yi, I'm taking the difference between our model state xi mapped using the observation operator and the observation yi, weighted by the inverse of the observations. Now, how do I get all these xi's? Well, if I go back to this things, once I define x0, so at this point, my xi would be this point on the blue trajectory, which I'm comparing with the observation yi. How do I get xi from x0? I need to run my nonlinear model. I run my model to see what the state is there and compare with the observations. And so we need to solve this function subject to the fact that these x's satisfy our nonlinear model. So this is a simple way of saying my x at time I plus 1 is some operator times my x at time step I. And this operator is essentially my atmospheric general circulation model, a weather model, an ocean model, a carbon model, whatever kind of model you want, which takes me from time I to time I minus 1. And so all we need to do is to find the x0, which minimizes this cost function. And that, by the way we've set it up, will give us the x0, which provides the best fit trajectory through the observations, consistent with our uncertainty, and also will stay close to the background, consistent with its uncertainty. If we assume that all the observations are at the same time, n equals 0 here, then we have what's called a three-dimensional variational assimilation, or 3D val. So the question is then, how are we going to minimize this? And this is the problem, because usually in weather or ocean forecasting models, this x is of size order 10 to the 8 and 10 to the 9. So we can't just write down the derivative analytically and say this is the solution. We need to find ways of efficiently solving this problem. And even a lot of the numerical optimization methods that are out there in practice don't treat problems of this size. And we have a huge number of observations. So what we're looking at is these numerical minimization methods, or gradient descent methods. So it's relevant to the question that was asked at the back earlier, where what we do, we can imagine if we had a state of size 2 of two variables in x. So this would be, say, the contours of our function j. We start with some iterates, some guess. We use that, use the value of the function in its gradient at that time to update it, and then at this new iterate, we calculate the function and its gradient again, and you get a new iterate, and so on. Where the general form is that this k is our iteration number, so we're trying to find x at time naught. And our x at time naught at the k plus 1 iteration is equal to our previous iteration minus some step length times whichever direction we're going in. So the phi tells us which direction to go in this, on this diagram, and the alpha tells us how far to go along that direction. And there are many, many different optimization algorithms to use out there. You would not write your own for this, because people spend their careers just developing efficient optimization algorithms, and there's lots of things out there, things like conjugate gradient or quasi-Newton methods. So this is just a general form of the kind of thing we want to do. The problem is, how do we calculate the gradient in most of these methods at each point, at each iteration? You need to calculate j and the gradient of j with respect to your initial conditions. So if we look at our function, we can calculate j but in order to calculate j, we need all these xi's, so we need to run the model over the time window. So in each iteration, to be able to calculate this cost function, we need to run our model over the whole window and be able to calculate all these xi's and calculate j. The question is, how can we define the gradient of j with respect to x naught, given this function? And x naught, remember, may have, say, 100 million variables, so the gradient of j with respect to x naught is a vector of 100 million values. The gradient with respect to each component. So we can't just perturb things and do things one by one. We need an efficient way of calculating the gradient. And this is where the idea of the Agile model comes in that Julia mentioned before. Julia gave a very nice pictorial representation of it. I'm going to present a little bit of the maths of where this comes from. I'm mainly presenting this for those who have seen these kind of things before. If you don't follow the details of the next two slides, the main thing is to get the idea of, and I'll say at the end of them, the practical application of how we use this. So the question is, given that on each iteration of this optimization algorithm, we need to calculate this function j and its gradient, how can we calculate the gradient in an efficient way? And we use what's called the method of Lagrange multipliers for those who've used it. So you set up what's called a Lagrangian, where we have the function plus a constraint. So we've said that our xi plus 1 must equal mi of xi. This is our model. So this term, if we're on the trajectory, is 0. And we set up what's called these Lagrange multipliers and add this as a constraint onto the cost function. And then the theory of calculus of variations tells us that necessary conditions for finding a minimum of this which satisfies our constraints is to take variations with respect to lambda and with respect to x. With respect to lambda gives us our original model back. When we take variations with respect to x, we get this equation here, where it's running, you'll see it's running backwards in time. So we've got something from time I depending on time I plus 1, which is why Julia said the adjoint model runs backwards. And what we have here, this m and this h, is essentially the transpose of our model. So what do I mean by that? And I'll go into more detail in a moment as an example for this h. But what we do, we take our nonlinear model, we find our linearization of it, so we differentiate our model, which gives us that capital M, and then we take the transpose. And this is what we mean by the adjoint model. Now, I don't have time to go into detail in exactly what that means. All I want to say is to get the idea here is that we can derive these operators M and these operators H from our original operators, our nonlinear model and our nonlinear observation operator. And once we do that, by running this model, which we call the adjoint model, from lambda I plus 1 at the end, when we get back to lambda naught, this gives us, as if by magic, again, I don't have time to go into the details, it gives us the gradient of our cost function with respect to all the different variables x. So if I was going to find the gradient with respect to, say, x1, x2, x3, I could perturb x1, perturb x2, perturb x3. So it would cost me 3 model runs in order to calculate the gradient, doing a forward gradient calculation. If I have 100 million, it would take me 100 million runs. The magic, so to speak, of these adjoint equations is by one run of this adjoint model, we get the gradient, the whole vector of the gradient with respect to all our variables at the initial time. And so that means that we can, by using this technique of deriving the adjoint model, we can easily calculate the gradient, so the cost function and its gradient on each iteration of our numerical optimization method. So if you don't follow the details of this, the main thing to understand about it is that we can derive this kind of model, the adjoint model, and this model allows us to get the gradient on each iteration so that we can use these numerical optimization algorithms. But what do we mean here by the linearization and its transpose? I just want to give a simple example. So this is the example we gave yesterday, where we had our x was simply consisted of the east, west, and south component of the wind, and what we actually measured was the wind speed. So our h operator, which takes our x and converts it to what we actually observe, was taking the square root of u squared plus v squared. What do we mean by the linearization of that? It's simply a vector where we take the differential of h with respect to each of the components. So dh by du and dh by dv, which if you work it out is equal to this. So that is the h operator, and then we can transpose this just by transposing that vector, and that gives us, that's what this h transpose operator would be on this previous slide. So you can see, although this looks a bit complicated, this h transpose and m transpose, for some examples, it can be quite easily to calculate, or at least the idea is there. All you're doing is differentiating these operators and then transposing them. And of course, that becomes more complicated when you have your full model or a radiative transfer model, but you can actually do this at the level of the code. I'll mention it more later, but you can actually do this differentiation at the level of your Fortran source code. So, where have we got to? We're trying to minimize this function where we've got the distance, measuring the distance to the background and the distance of the model trajectory subject to our model equations, the distance between the model trajectory and the observations over some time window. And we want to minimize this using a numerical optimization technique. And on each iteration, we need to calculate J and its gradient with respect to the initial conditions. So to calculate J, we need to run the nonlinear model to be able to calculate all these xi's, and we can do that. And to calculate the gradient of J, we need to just run the nonlinear model, which goes backwards in time, and one run of the adjoint model will give us the gradient of J. And on each iteration, we can therefore do this. So we have this kind of algorithm where we have an iteration x, we run the forward model. What's this observation increment? You notice that in the adjoint model, we have this h of x minus y, which needs to go into the adjoint model. But we need to calculate that when we calculate the cost function. So there's no point in calculating it twice. When we go forward, we'll calculate that and feed it into the adjoint model. So we calculate our forward model to calculate j of x, but we keep each of these hx minus y's and feed them into the adjoint model. We run the adjoint model backwards to calculate the gradient. So that means we have on this iteration our value of j and the value of its gradient. We feed those into our numerical optimization algorithm, which gives us a new iterate, and we keep going around here until we decide we converge or we've done enough work. So in theory, that's fairly straightforward to do. but it can be computationally expensive. So if you're running these gradient descent algorithms, I mean, a lot of the time when they run them in operational weather forecasting, they're running, say, 50 to 100 iterations. So that means you need 50 runs of your forward model and 50 runs of your agile model in order to be able to do this iteration. So the data assimilation really becomes a very expensive part of your whole weather or ocean forecasting process because you're running the model many, many times. Can we make this a bit cheaper? Well, there is one way of doing it, and this is really what allowed people to do things operationally, was by making it cheaper, is if we go back to the system we had before, we have the observations over the time window, and we have some background. Instead of just doing one solution to try and find the best trajectory through the observations, we just say, let's linearize around this background and try and find a small increment here such that we get something better within a linear approximation. Then we'll linearize around this new trajectory and find something slightly better, linearized about that. And then we'll linearize about the new trajectory until we get the final analysis. And this is what is known as the incremental version of 4D var. Now, mathematically, what does that mean? This looks a bit complicated, but I put it there for your benefit to look at later. Here, all we've done is linearize the original cost function. So instead of x, I've let x be the background, or be a first guess, plus delta x. So we're saying, say on here, I'm going to let my x here be, this is my first guess on this iteration, my first guess plus some delta x here, which I'm trying to calculate. And so we end up on each of these, for each of these intermediate black curves, we have to solve a series of linearized minimization problems where we have delta x, we're solving for delta x, where this d here is measuring the distance between each of those black curves and our observations, and we're just trying to find a small increment to make things slightly better. Subject to the fact that these delta x's now satisfy, instead of our nonlinear model, they satisfy the linearization of our model. Then once we've found that delta x, we add it on at the start, and we can run the nonlinear model again to get a new trajectory as on the previous picture and repeat the whole process. So these are called, each time we do one of these black curves is called an outer loop, and the solution of this linear problem is called an inner loop. Why does this make things easier? Well, what happens in practice is that they solve this problem at, for example, a lower spatial resolution and a lower, using a simpler model than the full system. So that you can make this inner problem much cheaper than if we were doing the full problem. Of course, it's then an approximation, but we can make it cheaper and then use an update on this outer step. And so the advantage of it is it has the inner loop cost function is now linear quadratic because we've linearized, so it's got a unique minimum. We can simplify the linear model using a lower resolution or a simplified physics to save computational time, and this is what is done in practice. It's equivalent to what's called, in the optimization literature, an approximate Gauss-Newton procedure, and this is something we've looked at in the past and shown about how we can prove something about how this can, when this converges to the solution of the true problem. And this is the method that's used in several operational weather forecasting centers, or a variation of it. So, for example, ECMWF or the Met Office use some variation of this. There's an intermediate thing, so we said 4D var uses the observations over the time window, 3D var uses just at the start of the time window. There's an intermediate, an improvement of 3D var called 3D FGAT, or first guess at appropriate time, which uses this incremental formulation. And what it does, it uses this incremental formulation, but where we have the linear model M here, it just replaces it with the identity. Now, what difference does that make? Well, when we're calculating this DI, so the difference between our observations and our current estimate of the state, Here we're using the full nonlinear model. So here we're still using something to do with the model dynamics, because to estimate, to look at the distance between our observations and our first guess trajectory on each outer loop, we're still using our nonlinear model trajectory, but we're not using the linear model to propagate the perturbation. And that means, first, it saves computational costs, and it saves development of this linear model, and in practice, you need the adjoint of this linear model. So it means that we have our nonlinear model so we can do this bit. 3D var would just assume this result at the same time. 4D var would assume this is not the identity, but 4D var requires the linear model and its adjoint. And by using this intermediate algorithm, we can avoid the development of the linear model and its adjoint, but still get some of the system dynamics into the assimilation. So some properties of 4D var. One of the advantages of it is it treats the observations at the correct time. And because of this, the fact that we're also using the dynamics means we can obtain more information from the observations. So for example, if over the time window, the temperature is increasing and our model can match that, that is giving us some information about what's happening rather than just doing things separately at each time. We can use something about the time dynamics of the model and of, say, the atmosphere or the ocean or whatever system in order to gain more information from the observations. The covariances are implicitly involved. I will come back to this a little bit tomorrow, but essentially we'll see later in the Kalman filter that we evolve this covariance matrix where we don't in the variational methods, but there is some implicit involvement. However, the standard formulation assumes that this model is perfect. So one disadvantage of this is if you think when we're comparing the model trajectory to the observations, we're assuming that the difference between them is essentially due to the observation error, this y minus hx. But of course, the longer we make the window, it may be that when we've run our model from the initial conditions, we've got errors in our model, and they're also contributing to the difference between the model and the observations. And of course, the longer the window, the more our model errors are going to kick in and be important. So in the standard formulation, we don't allow for this. But I'll come back to this tomorrow. There is a formulation called the weak constraint version, which is being developed to be able to relax this assumption. In practice, the development of these linear adjoint models may be complex. It can be done at the level of the code, so linearizing each line of code. But if you have a big complex model, it can be complicated. So the procedure is so automatic that if you have a well-written model and you've thought about this before, there are some automatic packages which you give it your nonlinear source code and it will produce your linear and adjoint model source code automatically. However, if you're doing this, say for operational things and you want something efficient, it may not be the case. So before my previous job, I worked at the Met Office and I spent several years, for example, just developing their linear and adjoint model. So it can be several years of a person's work. So that's 4D var and the idea of 4D var. And this afternoon, you will have some practicals on the Bayes theorem that I spoke about yesterday and on using 4D var. And I want to talk about another method, which is the Ensemble Kalman filter. And again, and this will be coming to the practicals tomorrow. So in the Ensemble Kalman filter, we simulate the observations sequentially. So we go sequentially. If you remember at the end of the last lecture yesterday, I showed the difference between sequential, so a filter and a smoother. Now 4D var is a kind of smoother. We're treating all the observations together. In the Kalman filter, we're going sequentially through the observations. It's a filter. We go by time, assimilating at each time. And we're going to use, essentially, this equation that we found yesterday and I started today's lecture with, which is essentially what the minimum of the cost function is if we assume everything's linear. But in this case, what we're going to see is, and it'll become clear in a moment, that the background state comes from the forecast of the previous analysis, But the thing about the Kalman filter, which is not the case in variational methods, is that the uncertainty in the background also comes from a forecast of the uncertainty on the analysis. So let me just set up the problem first, and then we'll look at a picture. We're going to assume, in the standard Kalman filter, we'll assume everything is linear. So we have a linear model and a linear observation operator. But here we're going to allow for model error from the outset. We're not necessarily going to assume the model is perfect. So our model is that xi at time I plus 1 is mi at time xi. But if I take the truth state at time xi and propagate it using the model, I won't get exactly the true state at time I plus 1 because there will be some error, because there's an error in my model. Now, I don't know what this error is, but I'm going to assume that I know its mean is 0, and I'm going to assume I know its covariance Qi. So then how does the Kalman filter work? Well, let's suppose we have some prior at the initial time, xb, and we have some uncertainty on that given by these red lines. So this would be our covariance matrix when we come to the 3D problem. And at the initial time, at different times, we also have observations with their uncertainty. So what do we do with the Kalman filter? The first thing is to say, well, at the initial time, I have this prior with its uncertainty, and I have these observations with its uncertainty. So I've got the equation that I showed on this previous slide, this linear equation. I can combine them and get the analysis at that time. So that's just using this equation here. I can combine the prior and the observations using their uncertainty to get the analysis at this time. Then what? Well, in order to go to the next time, I'm going to say, what is my background or prior going to be at the next time? I'm going to take my analysis at this time and make a forecast. And that will be my prior at this time. So the question is, okay, now I have at this time, I have my observation with its uncertainty, I have the prior. So if I have the uncertainty on this prior, I can combine them and do the analysis at this time. What is the prior uncertainty here? Now I could just use the same as I use here, and that's the standard way we would do things in the variational method. But what we actually do is to say, okay, what is the uncertainty on my analysis here? I can get an estimate of the uncertainty on my analysis, and I'm going to forecast the uncertainty on my analysis, and that's going to give me my uncertainty on my prior at this time. So now at this time, I have the observation with its uncertainty, and I have the prior with its uncertainty, and so I can use the same equation again to combine them and find an analysis. Then I want to do the next thing, so I need to go to the next observation time. I find again my uncertainty on my analysis, so then I can make a forecast from my analysis here to the next observation time and find the prior, but I can also forecast the uncertainty and get a forecast of the uncertainty or an estimate of the uncertainty at this time. So now again at this third time I have the observation with its uncertainty, the forecast with its uncertainty. I can combine them using the same equation and get an analysis, and so on. And I keep moving forward in time here. So if you think at each time, what do we need to do? We need to calculate the analysis, we need to calculate the uncertainty on the analysis, and then we need to forecast them both in order to get the prior and the uncertainty at the next time. So we have the following steps. First is to do the analysis at the time we're at. And this is the same equation, only I've broken it up with this K. Maybe I didn't introduce this name before. This matrix here that goes into the analysis equation is often referred to as the Kalman gain. But combining with this is just the equation I had before. So the first thing we do is to calculate this gain matrix and find our analysis at the time we're at. Then I said we need to find the uncertainty at the time we're at. And it turns out there's an equation for this. I don't have time to show the derivation of the equations, but this is the equation that it turns out to be. And then I want to forecast the analysis to get my next prior, and forecast the analysis error covariance, the uncertainty, to get my next prior uncertainty. And that's given by these two equations here. So to find my next prior, I just take my analysis and use my model, my standard model, to get my forecast. And again, it turns out if I want to forecast the uncertainty, I need to take the analysis of uncertainty, and this is the equation for the prior forecast uncertainty. It's if we have no model error, then this Q disappears. Otherwise, we have this Q in here. But these are the equations just so you've got them for a record. But all we're doing is what I said before. Do the analysis, calculate its uncertainty, forecast the analysis to get the next prior, forecast the analysis uncertainty to get the next prior uncertainty, and then we can do the analysis again at the next time. The problem is in practice, well, we've assumed that everything's linear in practice, where here it's not. And this error covariance forecast here, if M is an n by n matrix, then this requires of order n runs of your model. So if your model is of order, has 1 million variables, then just doing this step requires 1 million runs of your model. So for large models, this is impractical, even if your model is linear. But we can use this as the basis to design other things. And that's where the Ensemble Kalman filter comes in. We're going to approximate this step, but instead of doing our 1 million runs of the model, we're going to do a few runs of the model, a few what we call ensemble members. We're going to sample from this PA, run those forward, and say our sample forecast, take the covariance of our sample forecast, and they will approximate this PF matrix. And that's the way the Ensemble Kalman filter works. So the error covariance is approximated by an ensemble of model runs. So we have our analysis ensemble here. We have various analyses. We run those forward to get a forecast. And then the sample covariance of these forecasts essentially approximates our forecast error covariance matrix. That's the general idea. How does this work in practice? There are two main types of Ensemble Kalman filter. What we call the preserved observation or stochastic Ensemble Kalman filter and the deterministic Ensemble Kalman filter. So we'll consider both of them. I'll go through briefly the idea of them, and then tomorrow in the practicals, there'll be the opportunity to test out both of these. So what we do, we have an ensemble of states. So we've got an ensemble of analyses, let's say. So here, the brackets I indicates our ensemble member. So we say we have a whole load of ensembles, and we run the model using our nonlinear model to get a whole load of forecasts. When we get our forecast at the final time, we get our next observation time, we can form the ensemble mean. So the mean of all our forecasts. So that would be the mean of all these. And we also want to form what is the sample covariance of all these forecasts. And that gives us, what we do actually, in order to do this, we subtract the mean. So we subtract the mean from each of the ensemble members. I don't expect you to follow all the details now, but you have the equations here to look back at. We form a perturbation matrix where we subtract the mean from all the different ensemble members. Then we can show that our covariance matrix is given by this X times X transpose. Now, note in practice, why does this help? I said that PF might be our 1 million, in theory, a 1 million by 1 million matrix. In practice, we're doing a lower rank approximation to it, so we may have 100 ensemble members, for example, and so the actual implicit size or the rank of this matrix is only 100. So we're doing a small approximation to this. And then once we've got that, we can do our analysis step, again, using the same equation as before. Only we have to do something strange in this form of the Kalman filter. We don't just take our, sorry, this should be a minus sign in here. I'll correct that later before I put them online. We have instead of just having our y minus h of x, we perturb our y, our observation, according to the error statistics of its knowns. So for each ensemble member, we had a different perturbation to the observation within its error characteristics, its known error characteristics. Why do we do that? Well, it's in order to make things consistent. So in order to ensure that what we know holds, that our analysis error covariance, it depends on the prior covariance according to this equation, you can show theoretically that by perturbing the observations, we can ensure that this holds. If we don't perturb the observations, then this doesn't hold exactly, and so we get an incorrect representation of what our analysis error covariance is. However, by doing this, we also introduce some extra sampling noise, and we have problems of having to invert this low rank matrix. So although this is a way forward of doing things, it has some things that you need to play with and some uncertainties in terms of the way you actually implement it. And I'll come to more of these in a moment. The other form of the ensemble Kalman filter is what's called the deterministic ensemble Kalman filter, where I said this is the equation we know must be true from theory, and we want our ensemble to satisfy. Instead of doing this trick of perturbing the observations, we're going to design an ensemble such that this holds automatically. So the prediction step of doing all the forecast is the same as for the other ensemble Kalman filter, but the analysis step is slightly different. So what we do here is we take each of our ensemble members and apply the observation operator to transform them to observation space. So we now have perturbations of observations. We compute the mean of these and a perturbation matrix, or the difference of them all from the mean, in the same way I did from the x's before. And then we have an equation for the analysis where, without going into the details, this y, this perturbation matrix y, which is essentially our hx, comes into this k. So if you think in the previous one, we had our h times pf here, and I'm essentially taking h, and this y is going to be our y is going to be h times the square root of pf essentially. So this is going to be approximated by y transposed, which is what happens here. So that's why we're doing this in observation space. And then we have the analysis. Our set of analysis is equal to the forecast, it turns out, multiplied by this transform matrix, where the transform matrix is chosen such that this, as I said before, such that this equation holds, such that we have the right statistics in our analysis. Now, how do you choose this T? There are many different ways, and these lead to many different flavors of the ensemble Kalman filter. So we'll look at one or two tomorrow. I'm not going to go into the details now, but just to know there are many different forms of these. They're known as either deterministic Kalman filters, ensemble Kalman filters, or sometimes square root ensemble Kalman filters. And doing those different choices of this transform matrix lead to many different versions of these. So that's, in brief, the two kinds of ensemble Kalman filters, and you have the equations there to look into in more detail. There are two main problems when we're running ensemble Kalman filters that we need to really consider, and there'll be the chance to look at this tomorrow. So, in general, first one is what we call filter divergence, or that the ensemble collapses. So this matrix PF may be, say, in practice, if you've got, as I said, a system of size 1 million, it should be 1 million by 1 million matrix. And you're approximating these with, say, 100 ensemble members. What happens then is that as the ensemble runs, the variance of this PF is not large enough. In other words, it thinks, as the Kalman filter goes on, it thinks that the prior is more accurate than it actually is. And if you keep on running like that, it will keep on believing the prior more and more, until at a certain point it stops believing the observations, and the observations have no effect. And this is what's called filter divergence or ensemble collapse. So what do? Every time we do this step of forecasting, of calculating this PF, we just multiply it by a number. So we say we have our estimated PF from the ensemble. Instead of just saying our PF matrix is equal to that, we say it's equal to 1 plus something like that, where rho may be 0.05, 0.1, whatever. Now, this is what's done in practice. How do you choose this inflation factor? Well, to be honest, it's very ad hoc. And it's very, just trial and error and seeing what works. But it is known in practice, if we don't do this, then we will find in the end that our ensemble collapses and we have filter divergence. So, and again, in the practicals tomorrow, there will be the opportunity to play around with this inflation factor and see what happens if you have a small ensemble when you don't include inflation and when you do. The second problem is because of this matrix, because we're approximating it with a small sample, is that it's low rank. And what that can do, so this, remember, is representing the correlations between the errors in the prior at different points. But you can end up with spurious long-range correlations, which are purely there just due to sample noise. So, for example, the error in the temperature here in Italy is correlated with the error in the temperature in Australia, which we know is unlikely to be the case. It's just sample noise. So what do? In that case, we do something called covariance localization, where we take our estimated matrix, and we use this is what's called a show product, so an element by element matrix multiplication, not your standard matrix multiplication, just multiplying element by element, where essentially we have 1 where we believe the correlations to be true, 0s where we believe they're not to be true, and maybe some kind of tail off. So anything in the long-range correlations, we cut them off and we just set them to 0. And again, if you're running on a small ensemble, this is really essential to get this right in order to ensure that you don't have, for example, you don't want a temperature observation in Rome affecting your analysis of your temperature in Australia. You wouldn't expect them to be related. So you want that correlation, that cross-correlation, to be 0. However, where do you choose when to cut your, how far to cut off your correlation? How do you choose, what is reasonable and what's not reasonable? And again, this depends on your application and is a lot of trial and error and really what you believe about your system. So, I think this is a general point in all these data assimilation methods. You can easily write down the algorithms in a mathematical way, but when you actually come to implement them, you really need an understanding of the physics of your system and what you're doing in order to be able to implement them in the best way. Otherwise, it's very difficult to get something to work. And that's all. I've left there some references to do with this, but I'll stop there.
Okay. Any questions on that lecture? Yep.
So just a very general question, having heard a lot now about those methodologies. So where would you preferentially use something like this Fourdimensional approach and rather a Kalman filter approach? Okay,
it's a good question, and there's been many discussions about that, so which approach to use, and there's some papers written on it. It depends a little bit. The advantage, so there's advantages and disadvantages of both. So the advantage of the Kalman filter, for example, is that the ensemble Kalman filter is that all you need is your nonlinear model, which you already have. Whereas if you want to develop 4D bar, you need to develop your Agile model. So if you want to implement something quickly, at least the ensemble Kalman filter is something much easier to implement. However, it then has these problems to do with inflation and localization. I think with certain nonlinearities, it's been shown that the variational methods provide a better solution in terms of when things are slightly more nonlinear, although they're assuming linearity. When things get more nonlinear, they're assuming they're slightly better and they provide a more global solution, and therefore they have certain advantages in those cases. But there is really a mix as to what. The other thing is, of course, so one thing we've looked at is also thinking about whether you want to use observations sequentially or whether you want to try and use observations over a period in time altogether. So if you want to try and get the trends of something right using a whole load of observations together.
Okay. And maybe just a very quick question regarding this covariance localization. I suppose that would also vary for different variables, isn't it? So you would have to-
Yes. And in fact, that's a big question, because also one of the questions is, I mean, we've looked at, a lot of the time these assimilation methods, you transform things and you solve them in a kind of variable space where you where things are more uncorrelated, and then you can treat variables. One interesting thing is what happens when you have correlations between different variables. So we've recently been looking at coupled atmosphere ocean assimilation, and how do you localize sort of the error in an atmosphere temperature with the error in a ocean temperature. And there are a few ideas, and we've started putting a few ideas out there, but there are still questions about how to do these kind of multivariate things. Usually people just do it on the individual variables.
Okay, thank you.
Kind of following on from Connie's first point, would you always use the Ensemble Kalman filter over the Kalman filter because of the kind of computational advantages?
Unless the Kalman filter you would use if you've got a linear model and if you've got a very small system. So the Ensemble Kalman filter, you're using your nonlinear model in it. So if you've got a linear model, you could use the Kalman filter, otherwise not. But also whether you can afford to do this step here. Now, if you've got something like maybe 10, 20, possibly 50 variables, you could maybe do this step here. So if you've got a linear model in a small system, you can use the Kalman filter.
And how would you then select the ensembles for I imagine there's quite like a difficult process, but how do you go around selecting the ensembles for the Ensemble Kalman filter?
Well, what you do, you're assuming that you have some initial PF. So you assume that you've got some initial uncertainty. So like, for example, in the 4D bar, at the initial time, we had our background and we assume it has uncertainty. So what you can do is take your prior there and perturb it according to the uncertainty that you know, taking random draws consistent with the uncertainty that you have in what you know of the uncertainty, the covariance at that time. And then that was sort of your initial ensemble.
So the covariance matrix R is representing the error of the observations.
Yes.
But as we know, sometimes it's not that simple to go from model space directly to observation space. So there could be error in the forward operator. Is that error also represented in the matrix R, or is it elsewhere?
I will speak a little bit about this tomorrow, so that's very interesting. So in practice, you're right, this R matrix represents the errors in essentially, if I go back, let me go back to the R matrix essentially represents the errors in your h of x minus y. And so it's measuring errors in your y, but also errors due to your, as you say, this model operator h, and also to the difference in spatial scales. And so that will introduce correlations. Until now, what previously people have done is say, we assume R is diagonal, we know there should be correlations, so let's inflate the variances a little bit. Now people have started looking more and more into this, so we know that for certain satellite instruments, there are interchannel correlations, and so people have introduced, if you've just got a few blocks, few satellite channels, you can have a block of the R matrix which has some correlations. And in practice, what people often do as well is, because we don't know how to treat these observation correlations properly, is to throw away a lot of data. So 95% of the satellite data that we get is not used because we just don't know how to deal with the large amount of data in the weather prediction and to deal with these correlations. So there's a big research topic at the moment, and one we're working on in Reading, about how to represent the correlations in here, also allowing for the fact of, as you say, errors in this H operator. How you can quantify that, and second, how you can best represent that in your assimilation problem. But there's still lots of open questions there.